Imagine this. You're sitting in a meeting and the sales manager is pushing, saying, "We need to increase sales, but the factory can't keep up with demand. We're maxed out." Then all eyes turn to you. The question hits the table. How can we increase our extruder's capacity? What do we need to do? We can't keep running at this pace any longer. If you've ever been in that situation, you know the pressure. And that's exactly what we're going to tackle in this class. How do you squeeze more capacity out of your extruder without compromising quality? How can we make sure the production line runs smoother, faster, and more efficiently? This class is designed to answer all of those questions. By the end, you'll walk away with actionable strategies to increase your extruder's capacity and ensure your factory can keep up with sales without any more stress.
Today, we're diving into how to increase the real capacity of your extruder. Typically, this is where most feed factories hit a bottleneck, and it makes sense because the extruder is the heart of your production. It's where the actual product gets made. So naturally, the rest of the equipment in your factory can usually operate at a higher capacity since they're simpler in design. But the extruder, that's the complex part, and that's where things slow down. What I'm going to show you today is how to break through that bottleneck and bump up your extruder's capacity without sacrificing quality. Like I mentioned earlier, when we design a factory, we usually plan for the extruder to have the lowest capacity compared to other equipment. It's expected to be the bottleneck, but the issue that many factories face is that, in a lot of cases, the extruder isn't even running at its full design capacity. It's operating below the nominal capacity it was built for. So what we're dealing with here isn't just a bottleneck problem, we've also got an underperformance issue, and that's exactly what we want to fix. Because if we can boost the extruder's capacity, we're essentially increasing the overall capacity of the entire factory. Run your extruder faster and you're producing more. And that's the goal of this class, to help you maximize output at your equipment. By the end of this class, my goal is to give you the techniques and insights to help you run your extruder faster. So if your extruder is currently running at an average of 7 tons per hour, I want to equip you with the tools to bump that up to 9 tons per hour. If you're at 10 tons per hour, I want you pushing it to 12. The aim here is to boost your capacity, challenge your current limits, and help you get the most out of your extruder. All right, here's how we're going to roll with this. I'm going to give you a checklist and walk you through the key things you need to dial in if you want to consistently increase throughput while keeping your product quality top-notch. Throughout this, I'll point out what you need in place, how things should operate, and the common pitfalls to avoid so you can boost extrusion capacity without the usual hiccups, issues, or downtime, and still come out with a high-quality product. The cool thing here is, once you've got these best practices locked in, you're probably going to see improvements in product quality as well. Why? Because when you're running at high capacity, all the little details in the extrusion process have to be perfectly tuned. And when those details are optimized, better product quality is just a natural result. So by the end of this, if you implement the stuff I'll be talking about, you should not only be able to produce out more product, but it'll be better too. The first big win when we crank up production speed is a drop in operational costs, which is obviously great for us. You're producing more while keeping your operating expenses pretty much the same. Salaries, they don't change. The energy bill barely moves. Maintenance costs, about the same. But since you're producing more, all these costs get spread out over a larger output. And this is huge for the factory because it directly impacts one of the key performance indicators for the business. So running faster doesn't just mean more product, it's actually a smart financial move. We'll also be able to sell more products, not just because we're producing more, but because we've got a couple of new strategic options thanks to lower production costs. First, I could lower the price to make my product more competitive in the market. Or I could keep the price the same and hold on to that extra margin. That extra margin could either go straight into profits, or I could reinvest it back into the factory for improvement projects. Either way, this makes the business healthier. Everyone in the company is working toward making the product better and more competitive. And running the extruder faster, boosting throughput, is a key way to make that happen. The big question we need to answer in this presentation is, how do we increase extruder capacity? How do we run faster, increase throughput, and still maintain product quality? Quality is absolutely non-negotiable. We can't just speed up if it means the product falls below standard. There's no value in producing faster if what we're delivering is poor quality. What we need to do is find a way to maintain that high quality standard while also speeding up production. That's the balance we're aiming for. High quality products, produced efficiently and quickly. We can't just ramp up the extruder capacity and end up creating more rework. That defeats the whole purpose. If increasing capacity leads to poor quality products, we'll have to reprocess them, which brings additional costs. Things like repackaging and then reintroducing the product back into the process, diluting it with the good stuff. Even in the best case scenario, this lowers the overall quality, and that's not what we want. Plus, reworking means extra expenses, more energy, more maintenance, and basically repeating the entire production cycle just because we didn't get it right the first time. It's inefficient and costly. That's why quality has to come first. What I'm proposing here is a way to increase extrusion capacity while still maintaining that high standard of quality. All right, here's how we're going to tackle this. I'm going to give you a checklist and walk you through everything you need to check off to consistently run at a higher throughput while keeping product quality intact. Throughout this presentation, I'll break down what needs to be in place, how things should operate, and what to avoid so you can hit higher extrusion capacity without dealing with fluctuations, issues, or downtime, and still deliver a high-quality product. The interesting thing is, once you've got these good practices dialed in, you'll probably notice an improvement in product quality too. Why? Because when you're running at high capacity, every detail of the extrusion process has to be fine-tuned. And when you optimize those details, better quality is just a natural byproduct. So by the end of this session, if you implement everything I talk about, you'll not only have a superior product, but you'll also be producing it faster. The first thing to keep in mind is that your extruder's motor load sets the capacity limit. As you start pushing closer to that limit, the gap between the load you're using and the motor's maximum capacity gets smaller. Ideally, we want to reduce this gap, but here's the catch. If your motor load is fluctuating with constant ups and downs, there's a real risk of hitting a spike that pushes you over the motor's capacity. When that happens, you're looking at downtime, rework, and waste, exactly what we're trying to avoid. On top of that, when we push the extruder to its limits, other fluctuations can pop up in the process. You might see liquid inconsistencies or variations in material flow inside the extruder. These variations can have a direct impact on product quality, and that's something we absolutely don't want. Quality has to stay consistent even when we're running at higher speeds. All right, let's get into how we can boost your extruder capacity. But before we dive in, I want to make sure we're on the same page. I'm assuming you're starting off with a solid setup. That means you have a consistent flow of ground material coming from the grinding and mixing stages into the extruder, without any feeding issues. I'm also assuming that everything downstream, like drying and cooling, is running smoothly, right? If you're dealing with problems in those areas, no worries. We have classes that cover those topics. But for now, let's focus exclusively on the extrusion process itself. The first thing we need to zero in on when it comes to improving or increasing your extrusion capacity is avoiding fluctuations. Any hiccups in your process can lead to fluctuations in the motor load of your extruder. And since we're operating close to that motor load limit, these fluctuations can easily push the load beyond what the extruder can handle, resulting in shutdowns that halt the entire process. And we definitely don't want that, right? So our first goal is to minimize these variations as much as possible. To kick things off, let's focus on the quality of the mash entering your extruder. Before we even dive into the extrusion process itself, I need to stress that during a production run, which involves multiple batches, all batches coming from grinding, dosing, and mixing need to be consistent. It all starts with the quality of your raw materials. For instance, if I'm using fish meal with 10% fat in one batch and then switch to 12% in the next, I've just introduced 2% more oil into the mash, which is going to cause fluctuations. This really highlights how crucial consistency is right from the beginning. Now, beyond the raw material quality, the dosing process has to be spot on. If the recipe calls for 1,000 kilograms of wheat, and in one batch I dose 950 kilograms, while in the next I dose 1,050 kilograms, even if the wheat quality is identical, the difference in quantity is going to create fluctuations. The extruder operator might not change any settings, but the variation in material will still cause issues. That's why the dosing and mixing processes must be precise and consistent. Speaking of mixing, if I have poor mixing, let's say a coefficient of variation, CV, above 10%, I'm going to run into problems because the material won't be homogeneous. This lack of uniformity will carry over into the extrusion process, causing fluctuations in both the process and the product quality. And if I try to ramp up capacity under these conditions, those fluctuations are only going to get worse, leading to all kinds of headaches. So before we even get into how to increase extrusion capacity, we need to make sure everything from raw material reception to dosing, grinding, and mixing is correct and consistent. That's the foundation we need to build on. The very first step we need to take to operate at a higher capacity, safely, without risking poor quality products or causing downtime, is to minimize large variations in our process. So even before we start transferring materials, we need to make sure that the feed or mash being moved from the live bin into the conditioner is incredibly consistent. There shouldn't be any fluctuations in that part of the process. That's our first checkpoint. Now, there are two main methods for transferring material from the live bin into the extrusion process. The first is using a live bin itself. This is fantastic equipment because it features an agitator that keeps the material in motion, ensuring that the feeder screw is always full. We want to avoid any empty pockets in the feeder screw, as these will create variations in material flow. If sometimes the feeder has material and sometimes it doesn't, you can bet that's going to lead to problems. Another issue with the feeder screw is how compressed the material is inside it. Picture this. If your live bin is full, the mass of material creates significant pressure. But if the live bin is nearly empty, the pressure drops and the material being transferred becomes less compressed. That's something we need to keep a close eye on. So, ensuring a consistent flow from the live bin is crucial for maintaining stable operation and optimizing our extruder's performance. That's our target. That's our objective, right? To achieve this, you need to have a solid understanding of dosing, mixing, and grinding. It's essential to grasp the entire production process, because when problems arise, and they will eventually, we need to know how to tackle them head on. The good news is, we have more classes covering all these topics to help you get up to speed. There are two ways to control the feeder screw: gravimetric and volumetric. Gravimetric is always the more precise option. In this system, we use load cells on the live bin to accurately measure how much material is being transferred by the feeder screw. The speed of the feeder screw is adjusted based on the weight loss inside the live bin. This setup makes the system incredibly precise. We know exactly how much material is being transferred every single second, allowing us to adjust the feeder screw speed to consistently convey the exact same mass of material from the live bin into the conditioner. This level of control is crucial for maintaining a steady and reliable production process. With volumetric control, things are less precise because we're assuming the feeder transfers roughly the same amount of material each time. However, as mentioned earlier, the compression of the material can vary. If the live bin is full, the mash is highly compacted, and when it's nearly empty, the material is less compressed. To avoid these fluctuations, a practical approach is to keep the live bin at a constant level. This can be achieved by installing a level sensor. As soon as the material drops below a certain point, the sensor triggers the refilling process. Once the bin is adequately refilled, the sensor stops the process. By maintaining this consistent level, we also maintain consistent compression of the material, ensuring that the same amount of material is delivered into the conditioner. In short, the first step is to ensure a constant flow of material from the live bin to the conditioner, helping us keep everything stable and consistent throughout the extrusion process. Once we have established a constant flow into the conditioner, the next step is to ensure that the conditioning process is functioning effectively. Good conditioning is crucial because when the material exits the conditioner well cooked, it becomes easier for the extruder to handle. This ease of handling translates to a reduced motor load. A lower motor load means we're using less energy, which opens the door to increasing the extruder's capacity. To achieve effective conditioning, we need to inject enough water into the conditioner. Not just any water, but hot water. It's vital to use a spray system to atomize the water, allowing it to spread evenly throughout the mash. Additionally, we should incorporate steam at low pressure, ideally between 1.5 and 2.5 bars, to elevate the temperature of the mash to around 95 to 99 degrees Celsius. The closer we get to 99 degrees, the more cooking occurs, which also reduces the energy required during extrusion. This reduction in energy consumption not only helps us increase the extruder's capacity, but also enhances product quality. If you're interested in delving deeper into the conditioning process, we offer a dedicated class that covers this topic in detail. Now, let's shift our focus to the extrusion process itself and the key parameters that require our attention. It's essential to maintain stability in all parameters during both the conditioning and extrusion stages. To help with this, you can utilize online monitoring tools, like the one I demonstrated earlier in this training, to keep track of your process stability. For instance, take a look at the chart where the extruder motor load is displayed in red, revealing some fluctuations. You'll also notice slight variations in other parameters, such as feeder speed. While these small changes may seem insignificant, they can significantly impact the overall process. Our objective is to minimize these fluctuations. The more stable we can keep everything, the better our results will be. With online monitoring systems in place, you can spot these fluctuations and understand their origins. This insight is crucial for investigating and addressing any issues that arise in your process. Whether you're using automated systems or managing things manually, having a clear view of your operations helps you pinpoint where improvements can be made. So let's dive into the critical aspects you need to observe in your factory to achieve stable production, reduce the motor load on your extruder, and create room for increasing your extruder capacity. When we discuss extruder parameters, we're focusing on elements like liquid injection, whether it's water, oil, or other additives introduced into the extruder. The best practice here is to meticulously measure everything you're injecting and correlate it with the extruder's throughput. For instance, let's say the extruder is operating at a capacity of 8.7 tons per hour. Every parameter being used is linked to that throughput. In this example, if we're injecting 10% water into the conditioner, that amounts to 870 kilograms per hour. Similarly, if we add 1.2% water in the extruder, that figure is based on 100% of the extruder's capacity. The same approach applies to oil. In our case, we're adding 9% oil, expressed as a percentage of the extruder's capacity. For steam, we're injecting at 0.7%. The key here is that everything introduced into the extrusion process is consistently compared to the current throughput. Now, here's why this is so crucial. It doesn't matter what capacity you're operating at. If you move from 8.7 tons per hour to, say, 9 tons per hour, the system can automatically adjust all parameters to maintain the same proportions of liquids being injected into the extruder. For instance, if you need to maintain that 10% water in the conditioner while increasing your throughput to 9.2 tons per hour, the system will recognize that and adjust the water injection from 870 kilograms to 920 kilograms per hour accordingly. This way, all parameters are automatically adjusted, relieving you of the burden of manual calculations. You only need to focus on maintaining the right proportions, which simplifies the process significantly.
To clarify, let's check how water injection is working here. We started with an extruder operating at 8.7 tons per hour, injecting water at 10%, which amounts to 870 kilograms per hour. If we decide to increase the capacity to 9.2 tons per hour, the beauty of the automation system is that it uses the extruder's throughput as a reference for liquid injection. So when you set the extruder to 9.2 tons per hour, the system automatically adjusts the water injection to maintain that same 10% ratio, increasing it to 920 kilograms per hour. This principle applies consistently. If you were to increase the capacity further, say from 9.2 to 9.5 tons or even to 10 tons per hour, the system would seamlessly adjust the water injection to 950 kilograms and then to 1,000 kilograms per hour, respectively, to maintain that 10% ratio. This automation is incredibly beneficial for avoiding the trial and error approach often used when increasing extruder capacity. Operators no longer need to manually tweak each parameter, reducing the risk of product quality issues. Previously, many operators would run the extruder at lower capacities just to maintain stability. Now, with this automated system, they simply set the desired throughput, and the system takes care of adjusting all necessary parameters to keep everything balanced. This not only enhances efficiency, but also ensures product quality remains consistent. When it comes to increasing extruder capacity, patience and a step-by-step approach are essential. For example, if you're currently running at 8.7 tons per hour and your target is 12 tons per hour, you wouldn't just jump straight to 12. Instead, you'd follow a gradual process. 1. Incremental steps. Start by increasing from 8.7 to 9 tons per hour. 2. Stabilization period. After each change, wait a few minutes to allow the entire process to stabilize. This is crucial to monitor any impact on product quality. Third, monitor changes. During this stabilization period, observe how the adjustments affect the process. Even though you're maintaining the same proportions for liquid additions, operating at a higher capacity will change the pressure within the extruder. This can also affect friction levels and lead to fluctuations in liquid injection. Once you've ensured the process is stable at 9 tons per hour, you can move to the next step, increasing to 9.5 tons per hour. Again, allow time for stabilization before proceeding. Repeat this process, incrementally increasing the capacity while allowing time for each change to settle until you reach your desired capacity. This methodical approach not only helps in maintaining product quality, but also ensures that any unforeseen issues are managed effectively. Another challenge we encounter when ramping up our extruder capacity is backflow. As we increase that capacity, the chances of backflow occurring inside the extruder also rise, and that's a problem we definitely want to avoid. Why? Because backflow can send our extruder motor into a roller coaster ride of fluctuations, causing the motor load to spike. And when that happens, we're at a high risk of downtime since the motor load can exceed its limits. But don't worry. There are effective strategies we can implement to keep backflow at bay and ensure a smooth, uninterrupted process. By taking proactive measures, we can significantly reduce the risk of backflow and maintain steady production levels. Here are a few things we can do. To significantly reduce the risk of backflow in your extruder, the first thing you should focus on is ensuring that your wear parts are in good condition. For instance, if your screw is worn out, like in this example where the screw flight has become rounded and there's noticeable pitting, you'll end up with a larger gap between the screw and the barrel. This increased gap makes it all too easy for material to flow backward toward the conditioner, especially when you're pushing higher capacities. As the extruder fills up, pressure builds, and that's when backflow is most likely to happen. To combat this, it's essential to keep the gap between the screw and the barrel as small as possible. If you're noticing backflow issues, one of the first things to check is the condition of your wear parts. For most extruders, if the gap between the screw and barrel exceeds 5 millimeters, it's definitely time to consider replacing either the screw or the barrel. Keeping this gap minimized is crucial for maintaining proper material flow and preventing backflow. Taking care of these components not only improves your extruder's performance, but also helps you operate more efficiently, keeping your production running smoothly without unnecessary hiccups. Another effective strategy to prevent backflow is by using larger shear locks. Here's how it works. When you incorporate larger shear locks, like the one shown in this picture, they create a restriction that slows down material flow. This restriction builds up pressure behind the shear locks, causing the material to accumulate and form a barrier. So when the material tries to move forward and faces the pressure, it hits this barrier and can't flow back toward the conditioner, effectively stopping any potential backflow. On the flip side, if you're using smaller shear locks that don't provide enough resistance, the material can easily shift backward when it encounters high pressure from the extruder, especially when you're operating at higher capacities. Without that crucial barrier, backflow becomes a real risk. In summary, if you want to effectively prevent backflow, particularly when pushing your extruder to higher capacities, opt for larger shear locks. These locks create necessary barriers along the extruder, ensuring that material flows smoothly forward and minimizes the chances of backflow. This not only improves the stability of your operation, but also enhances overall efficiency. Up to this point, we've focused on factors that help reduce motor variation, allowing us to operate closer to the motor load limit and ultimately increase capacity. But what if your extrusion process is already stable and you're still looking to push that capacity even further? In this case, we need to shift our attention to reducing the motor load itself, not just stabilizing it. One straightforward method to achieve this is by increasing your extruder screw speed. If your extruder is equipped with a variable frequency drive VFD on the main motor, you can easily ramp up the speed. For example, if you're currently running at 50 Hz, you might consider bumping it up to 55 Hz or even 60 Hz. By increasing the screw speed, you expedite the transportation of material through the extruder. This results in the extruder being less full, which reduces the resistance or force acting on the motor, consequently lowering the motor load. With a reduced motor load, you can safely push your extruder to operate at a higher capacity. However, be mindful that increasing the screw speed can cause more expansion of your product. Therefore, it's essential to assess whether your process can accommodate that extra expansion. If expansion isn't a concern, this strategy provides a quick and effective way to decrease motor load and boost your production rate. Another effective way to reduce your extruder motor load is by optimizing your extruder profile for a gentler operation. Take a look at the factory examples shown here. These extruders feature a very aggressive screw profile. They utilize a double flat screw followed by mixing elements and then a single flat screw along with large shear locks in between. While this aggressive design helps with material processing, it also creates significant restrictions and increases the workload on the extruder, ultimately limiting your capacity. To achieve the best results, it's crucial to strike a balance between preventing backflow, ensuring product quality, and and minimizing energy consumption. By redesigning your extruder screw to be gentler, you can significantly lower the motor load. This gentler approach reduces resistance within the extruder, allowing for smoother material flow and decreasing the overall energy requirement. With a reduced motor load, you not only free up capacity, but also enable your extruder to operate at higher production rates without risking overload on the system. This optimization can lead to improved efficiency, better product quality, and greater overall output, making it a smart move for any feed production facility looking to maximize performance. Another useful tip is to start injecting oil into your extruder. You don't need to go overboard, just 0.5% of oil can work wonders by lubricating the components as the material processes inside. With this added lubrication, the dough becomes less viscous, which reduces shear and subsequently lowers the motor load. As your motor load decreases, you can ramp up your extruder capacity. In most feed production scenarios, you typically need to inject some oil during the coating process. For instance, if you need to inject 5% oil during coating, you could take 1% of that and add it to the extrusion process. This means you'd inject 1% of oil during extrusion and save the remaining 4% for coating. This way, you're still using the same total amount of oil. You're just distributing it differently. However, it's best to keep the oil injection to around 2% to 2.5% inside the extruder. Going overboard can lead to too much lubrication, which may negatively affect expansion and result in quality issues. If you inject too much oil, your product could end up fragile and lose strength. But by incorporating just 0.5% to 1% of oil during the extrusion process, you can effectively reduce motor load and boost your extruder capacity, enhancing your overall production efficiency. In this presentation, we've talked about ways to increase your extruder capacity, and with all these changes, you might need to tweak your die opening area too. For example, if you start adding oil or adjusting your screw profile, your product might not expand as much as it used to. In that case, you might need to block some die holes or reduce the number of them, but it could go the other way. If you're running at a higher capacity and there's more pressure behind the die, you might need larger holes or more of them, especially if you're using bigger shear locks or raising the conditioning temperature. Like we mentioned in the extruder die class, adjusting the die opening area is key to getting the right expansion and bulk density. So after making all these tweaks, just keep an eye on your die and see if you need to switch to more or fewer holes depending on how your product is coming out. At the beginning of this presentation, I mentioned that one reason we often don't operate the extruder at the desired speed is due to process variations that could push us beyond the motor load limits. When that happens, the motor shuts down, leading to downtime and generating rework waste. Our goal now is to run the extruder at the highest possible capacity, so we need to ensure that the automation system controlling the extruder can protect it in case of issues. One approach to safeguard your extruder is to implement operational limits. For example, if the motor load reaches 90%, the system could automatically increase the screw speed slightly. This minor adjustment can help reduce the motor load, keeping us below the critical limit. If the motor load reaches 95%, indicating we're very close to the limit, the extruder could bypass the chute between the conditioner and the extruder. This would stop material from falling into the extruder, allowing it to empty out, thus reducing the motor load. In the event that the motor load still rises, potentially due to backflow or other issues, we could reach a point where at 100% load, the system starts injecting oil and water to make the dough more fluid and lubricated. While this might lead to producing rework, the primary goal here is to protect your extruder and avoid extended downtime. By implementing these safety features, we can prevent scenarios where the extruder gets jammed with material, which can harden and require hours to clean out, ultimately slowing down production. These protective measures act as safety gears to maintain smooth operation and minimize the risk of significant downtime. Alright, that's a wrap on how to boost your extruder's capacity while avoiding common pitfalls. We've gone over key strategies like optimizing feed flow, maintaining your equipment, and ensuring you're getting the most out of every run. With these techniques, you're well on your way to running a smoother, more efficient extrusion line. But if you want to dive even deeper and maximize your factory's potential, I've got something that can really help. My complete extrusion course for feed factories gives you all the tools, insights, and expert guidance you need to increase capacity, reduce downtime, and take your production to the next level. This course is packed with strategies that will make a tangible difference in your operations. So if you're ready to unlock the full potential of your extruder and get more out of every batch, all you have to do is click in the button down below and join the course today. Thanks for sticking with me, and I'll see you inside the course.